let's get started. We closed the chapter of large networks, which was only about accuracy. So you had as much compute, as much data in front of you, and all you cared about was getting the best performance out of your model, regardless of the cost. So now we are going to start worrying about the cost. And first of all, we're going to start with making our models smaller, perhaps, make them more efficient in terms of the number of parameters they're using, in terms of memory, in terms of computation. And this is usually that you don't see in academia. Small networks, we don't really care about them that much. But when you go to industry, then these are really important questions. You train a large model on as many GPUs, TPUs as you like, but then in the end, you want to take that model, the trained one, to the customer. And the customer has smaller devices, like a cell phone, or it's a drone, or it's a robot, or it could be a self-driving car. And that's why you need to make your models smaller and start to worry about the computational cost of your deep neural networks. So that's the big picture. The first paper is about distilling the knowledge, and there are multiple ways of achieving that, achieving smaller networks. One of them is distilling the knowledge in a large neural network, in a smaller one. So the video is online. That was your exercise to watch it. Do you have any questions about it?
Hi, I have a few questions about this section. So first, I just want to make sure I understood it correctly. The cumbersome model was trained initially, and then the distilled model is still trained with the same data, but with a corrected loss function with the already trained prediction in that, correct? So it's still using the same data, but different loss function.
Not really. So one cool thing about knowledge distillation is that now you have a neural network. Let's start with the large neural network, the cumbersome model, and let's train it on some data. That model, the cumbersome model, is going to learn something from your data in its parameters. Okay. Now you can actually go ahead and generate as many artificial data as you like from this larger model. It could be your training data, or it could be some other data that are not labeled. Maybe you have some other images, but you haven't labeled them. You can push them through your cumbersome model. That's going to give you these probabilities. And then you're going to use those probabilities to train the smaller model. And at the same time, these could be the data that are already in your training data that you use to train the cumbersome model.
So in that case, I do not need to know the ground truth for the new data for my small model. I just want to have the distribution of the probabilities match as close as possible. And that's how it learns, right?
Yeah, exactly. So all you need to know is what are the predictions of your cumbersome model. So we are going to use the predictions of the cumbersome model to train a smaller model. And what is the difference? If I give you an image, you can have a labeler giving you the corresponding label. Now you have pairs of input-output, input images, output labels. Or your labeler could be the cumbersome model. You give it an image, and not only it's going to give you the correct or its prediction for the correct label, it's also going to give you predictions for every single other class. So some of them are cats with this probability, that image is a cat, with the other probability, that's a dog. And not only you are learning from the positive aspects from the cumbersome model, you're also learning from its mistakes or wherever it is not that confident. So does that make sense?
Yes, that makes sense. And when we make inference with the distilled model, just set the temperature to be 1 as normal, because the loss function is actually does not care about the temperature, correct?
The loss function that you're writing here cares about the temperature. And why do you actually set the temperature to be higher than 1?
It's to preserve the classifications that are not the top class, that the one is the mistakes.
Exactly. So you want to amplify the mistakes, or you want to amplify the confidence of the cumbersome model on its mistakes so that the smaller model doesn't ignore them. Okay, so it starts learning from it, but then once the learning is done, you can set the temperature back to 1, because in the end, you want to be pretty sure, you want your model, the smaller one, to be pretty sure about its predictions. Okay.
And during the training, how high is a ideal setting for the temperature, or is that to be experimented out?
That's a good question, and it depends on your data. Setting the temperature is a hyperparameter. So in the end, you're going to look at the performance of your smaller model on a validation data, and then you can use that to set the temperature properly. And this changes from data set to data set. For ImageNet, the temperature might be different than perhaps doing the same thing on data coming from languages, text or speech, or some other sorts of image analysis. Okay, so it's data dependent.
Okay, got it. I have one last question about this one is how do we get the sigma, the sum z's and the sum v's both equal to 0? Is that like manually controlled?
Yeah, this is approximately true. It is not perfect. So you are waving your hand a little bit here, and that's why this is approximately correct. Under the assumption that this is true, and another assumption that T is large enough, and we don't know what is large enough, that depends on your data, then distillation is equivalent to matching the logits using mean squared error. So you're trying to match the logits of the small model to the big one. That's to give you more intuition. But this is not a bad assumption, because from one layer to the next one, even the last layer, you can use batch normalization to make this happen.
Yeah, that makes sense.
Approximately make this happen. But this is just to give you more intuition. So distillation is definitely more powerful than matching logits. It's more than that. Under some restrictive assumptions, you're going to get matching logits. Okay, any other questions?
Yeah, I have a question. So usually we obtain a big model, a cumbersome model, and it was trained using temperature 1, but then we generate a bunch of training data using that model. So we feed it a bunch of images and we obtain probability distributions at the end, but we use a higher temperature to generate those probability distributions, say T equals 100. So how do we change the temperature of an already trained model? And I feel like this is more of like a practical coding question, but if we already have a pre-trained model, is it easy to go in and change the activation of some layer in a model?
Yeah, actually in PyTorch and TensorFlow, you can actually say, I want to look at my neural network from the first layer up until the 10th layer or the last layer before the softmax. Okay, so you can actually detach models or detach parts of your models. So this is very common.
Okay, that's cool. Thank you.
Actually, in PyTorch, there is this hooks that you can use. Actually, you can separate every single individual layer from your neural network. And here you can just cut your neural network up until the logits. Don't push it through the softmax. Just don't do the last layer. There is a question in the chat. Could you get a similar benefit from starting with a small network and iterating distillation over a couple of small network, or should you always start with a large network? So that's actually a very good question. When we go and we do this idea that you have in your head, it has a name. It's called label propagation. And this is good when you want to do semi-supervised learning. Maybe half of your data set is labeled, the other half is not labeled. You first train your model on the labeled part of your data set. You use the predictions of your model to label the corresponding part that doesn't have any labels. So you just use the predictions of your model. Now your entire data set is labeled. Some of them are real labels. Some of them are labels that you generated yourself. And then you retrain your model on that. And then you keep reiterating. And that's called label propagation. It's a technique for semi-supervised learning. So does that answer your question? Okay, perfect. Any other questions? Not only you can do knowledge distillation, but you can actually combine multiple models together. So this is a very good technique to know about. You can have a generalist model, and then you can have specialist models for some of the subcategories. And then you can actually combine the two, or combine all of these models together to make a prediction. Any questions about this? This is a nice idea. Any questions about it? This is not related to knowledge distillation, but it is actually a model ensembling technique. This could actually give you your cumbersome model. So to recap what is happening here, you train a generalist model. It is good at classifying cat and dog and other types of categories, large categories, but it's going to confuse between a tea party and an Easter or bridal shower. So it's going to confuse those subcategories, fine-grained details. PG, you already, it's a generalist model. You already trained it on your entire data set. You look at its confusion matrix. You're going to do some clustering on the confusion matrix to come up with these confusions. What is your neural network confusing? Then on each one of these subcategories, you're going to train a specialist model. So a specialist model 1 is going to be corresponding to tea parties, Easter. So it's going to specialize in that category. Another one is going to get specialized in different types of cars. Now here's the question. It's now testing time. Somebody gives you a new image. You're going to take that image, push it through your generalist model. That's going to give you PG. You take the same image, push it through every single specialist model. You're going to get the predictions PM. Now what you're going to do is you're going to solve a little bit of optimization during inference. You're going to find the best Q. And how do you find it? You want your Q to be as close as possible to the predictions of your specialist models. It should be as close as possible to the predictions of the generalist model. Once that little optimization is done, then you're going to know the corresponding label for that new image. So I think this part wasn't that clear in the video. It should be more clear now. Any questions about it?
So is the generalist model like a single big category, or can it be like several? Can it be like either cat or dog, and then we'll go into deeper look at both cat and dog, or is it just a one type of things?
No, the generalist model, you train it once on your entire data set, which includes tea party, Bridges, Toyota Corolla, different types of cars, cats, different breeds of dogs, different breeds of birds, etc. So you just train a single model first. Once you train that generalist model, it's going to confuse. Maybe it's good at telling the difference between a cat and a dog, but it's not going to be good at telling you what type of dog that is. You're going to look at its confusion matrix. So it's confusing tea party and Easter, and it's saying that they belong to the same category. To my eyes, they are the same. But now you're going to look at these fine-grained categories, and then you generate specialized models for every single subcategory that you have. Okay, so one of your models is going to specialize in telling apart a Toyota Corolla and Opel Astra. Now you have many models, and they have the same parameters. They have the same size. They are actually initialized. The specialist models are initialized with the parameters of the generalist model. So there is only one generalist model, many specialist models, and they're all trained. During testing, you just need to know what is the corresponding Q, what is the corresponding prediction for it. So does that answer your question?
Yes, thank you.
Yeah, sure. The question is, can this easily become a large network if we suddenly have a lot of specialist models and become expensive? Yes, absolutely. So this is going to give you your cumbersome model that you can then use to distill its knowledge in a smaller model. The idea here is that you can have very large models in production. Okay. Any other questions? Okay, perfect.